Hello everyone, my name is Andrei. I'm the founder of Unleash Engineering and my background is in automotive engineering. With over 16 years of experience in R&D and project management, I have a proven track record of delivering innovative projects for the automotive sector. I have worked so far with many stakeholders including automotive OEMs and Tier 1 suppliers like tire makers, so I know the challenges related to both part and system design engineering. As we know, to validate tire designs, manufacturers must test tires physically or, in the best case scenario, by using virtual technology. At Unleashed Engineering, we generate value by streamlining the R&D of smart tires for electric vehicles. We do this with modern engineering and effective and efficient data management. Before getting deeper into the R&D topic of this presentation, we must ask ourselves why we need sensors in tires. Well, sensors can solve a few tire-related challenges: tires logistics throughout the value chain, tires environmental impact at end of life, and vehicle dynamics performance improvement. We already know that tires data and physical location are a challenge for both the logistics and the environmental impact of the tires at the end of tire life. So, the solution is to have better tire data management and traceability of tires from manufacturing through all value chains until the end of their life. Okay, but who's interested in this traceability? You may ask yourself. I think we all are, especially if we want to leave a better world after us. Another motivation for having sensors in tires is to improve vehicle dynamics performance. It is well known that current LiDAR and radar sensing technologies mounted on vehicles do not feel the road. So, the solution is to move the classical TPMS sensors from the rim's valve to the tire's inner liner and add extra features for data recording and transmitting in real time to other apps relevant data. I guess we all want a safer ride and handling of our vehicles, and we should all be very excited about these solutions that could be potentially provided by having smart tires on our vehicles. Next, we must ask ourselves where we can mount, insert or attach the various sensors to a tire in a safe manner. If we look at the cross-section of a tire, we can identify two potential mounting scenarios: on the crown area under the tread or in the sidewall area. One of the engineering challenges is identifying which of these two areas is the best place for mounting the sensors in tires, considering that both areas have steel components, the bell package in the crown and the bead in the sidewall respectively. We also have different stiffnesses in the two areas of the tire cross-section and potentially different interferences of the sensors because of the steel components. It is already known that the steel may interfere with the radio frequency signal that the RFID sensors can send. If these sensors are misplaced, there are some risks of inappropriate readability by the RFID reading device. To eliminate the readability risks, on the one hand, electromagnetic simulations can be used to identify the best position of the RFID sensors with respect to the tire carcass. On the other hand, to eliminate the mechanical risks, structural simulations can be used to investigate the impact of adding these sensors in a tire from a structural perspective. Our focus is further on a numerical model for the structural analysis of a tire with two potential sensors, TPMS and RFID. Therefore, we must ask ourselves what is needed to enable the structural analysis at the system level to mitigate the risks of structural failure after adding new sensing technology on top of the old tire technology. Because of various limitations in the legacy engineering loop, we must design a new engineering loop for an upgraded virtual development. More specifically, we must rethink the tire engineering process so that it can start from the complete 3D tire design and allow system design engineering in the 3D space. Any smart tire technology engineering can be envisioned effectively and efficiently only if we allow the 3D part, subsystem, or system design engineering to align with other approaches from the automotive sector. The last question we must address is how can we enable a more effective and efficient tire system engineering loop that allows engineering at the 3D tire system design level? And the answer to this last question is quite straightforward. By establishing a novel and accurate numerical tire model creation workflow for engineering and innovative digital methods for testing instrumented tires. The workflow is appropriate for modeling and analyzing any tire design, including smooth, ribbed, and complex threaded tire models. It also has extended applications in R&D projects for tires with various beyond tire technologies, and it enables any 3D tire system analysis, including automations. Thus, we can engineer both old tires and new sensing technologies simultaneously, which is a must in the new case mobility context, which stands for connected, autonomous, shared, and electric vehicles. So, how can the sensors be mounted in tires? In the first mounting scenario, the electronic system of a special sensor, including a potential TPMS sensor and maybe also an ID tag, could be encapsulated in a sensor container that could be further attached to the tire's inner liner. Therefore, we need to be able to model the new digital tire system formed by a tire model and this new special sensor in an effective and efficient way. In the second mounting scenario, the electronic system of a special sensor, including a potential RFID tag and two antennas of different lengths, could be encapsulated in a rubber patch that could be further attached to or embedded in the inner line of the tire. As in the first mounting scenario, we need to be able to model the new digital tire system formed by a tire model and this new special sensor by using new numerical features to define the model. The next natural question is how to approach modeling in the new digital era. Where to get started? What is more important? The knowledge iceberg becomes bigger and bigger as tires transform into vehicle gadgets and vehicles become computers on wheels. In the new digital era, every product becomes smart and connects in some fashion to the big world of the internet. In the case of the new tire engineering challenges, it is all about changing the paradigm. As new features are added to the tires, new performance criteria are to be considered on top of the old criteria. Therefore, it is not enough to master the classical tire science knowledge, which starts from knowing which tools to use for virtual modeling and relies heavily on understanding the tire from a mechanical product and performance perspective. We must now learn about new tire electronics engineering science and how the latest electronic devices, represented by various sensors, could match seamlessly with the old-fashioned tire rubber and reinforced mechanical parts. When it comes to system modeling and setting it up, a few aspects must be considered carefully regarding the geometry, discretization method, and setting up the right boundary conditions to make the system work faultlessly. In this case, the special sensor, or what we can call a generic TPMS sensor, has been modeled by including two potential ID tags at two different locations. After modeling, it was attached to the inner liner in the middle of the ground or in the middle of the tire cross-section. Also, two acceleration sensors have been modeled on the ID tags to assess the acceleration levels during the footprint events. In the second mounting scenario, the special sensors or what we can call generic RFID sensors with antennas, have been modeled in 4 variants, each including a potential RFID tag and 2 antennas on each side of the tag. After modeling, they were embedded in 4 rubber patches, which were further attached to the sidewalls on each side of the tire. 2 different positions have been used with respect to the bid to identify the worst case for the embedding position and also to evaluate the antenna's geometry's impact. As we can see, different element types have been used for discretization and to reproduce the physical model in the virtual world. Also, 2 different lengths for the springs representing the antennas have been considered, a longer length and a shorter one. Another aspect of our virtual tire simulation workflow is how to make it work at the system level, considering that we have added new components to the tire besides the classic rubber and reinforcement materials. By new components, I mean the sensors. The traditional simulation workflow in which we start from a 2D tire design model to simulate the tire inflation in 2D and use various restart simulations to simulate the 3D tire vertical loading and rolling has some significant limitations. In the new 3D tire system model formed by a tire and a beyond tire technology, all boundary conditions must be redefined and applied to the new system. Therefore, we must rethink a new simulation workflow after the 3D model creation step is completed. The tire inflation, loading, and rolling are applied in a single simulation step.
Now, the natural question that follows is, does the new system simulation workflow work for a smart tire with sensor system mounted on the inner liner? Yes, it does work. As we can see, by looking at these simulations videos with various focuses, 3D perspective locks, and cross-sections in the real-time simulation, the system model works faultlessly in the first tire system model scenario. Does the new system simulation workflow work for a smart tire with the sensor system mounted on the sidewalls too? As we can see, it does work. It has the same tire size, inflation pressure, vertical loading, but with the sensor mounted in the sidewalls, as described previously in the second scenario, and with updated boundary conditions. The structural analysis can be further conducted by focusing on only one variable, like stress components in the global perspective, for instance. The structural analysis captures the so-called footprint passing events. As we can see in the case of the second mount scenario of the sensors, the system simulation captures the passing of the sensors through a highly stressed area each time it passes through the footprint event. To further speed up the numerical analysis, we can design automations to post-process huge amount of FEA data. This is another example of how we can look at the simulation data. As we can see, multiple variables can be considered when analyzing any dynamic loading scenario, starting from different stresses and strain components and closely monitoring other output parameters like contact pressure in the footprint or footprint area. The same automations for post-processing of FEA data can be considered when analyzing the interaction between tire and sensor components and their impact on each other. Thus, we can optimize the position of the sensors in the tire so that the damage risk of the both parts are mitigated. The structural analysis of the first sensor mounting scenario can be further supplemented by embedding other sensors like acceleration sensors and by analyzing their signals in real time. Thus, we can run very big DOEs and cover various load case scenarios to study the impact of dynamic parameter variations. Any inflation pressure, tire loading, and speed, for instance, as well as any other parameters like tire slip angles or tire slip ratios can be considered. Also, design sensitivity analysis can be conducted by adjusting the position of the embedded acceleration sensors inside the generic TPMS sensor. As we can notice, the acceleration signal is sensitive to the location of embedding of the sensor. We also expect to capture this sensitivity when tire design changes, but more study is required to get more data. The structural analysis of the second sensor mounting scenario can be further supplemented by monitoring the elongation of the sensor's antennas. The same four loading scenarios results are presented here, and we take each spring elongation signal and monitor it in real time. As we can notice, there is a slight change in the signal shape for the spring located at the back of the rolling direction. Looking at the signal shape of the springs located lower, or better said, farther away from the tire's bed, we notice higher elongations. This perfectly correlates with the high strain areas of the rubber patch in which the sensor springs are embedded. A similar observation is valid as before for the signal shape of the spring located at the back of the rolling direction. A fourth general observation for the generic RFID sensors with smaller antennas but with a denser coil base is that the elongations are smaller regardless of what position of the springs we consider. The second observation is the same as in the first sensor case. There is a slight change in the signal shape for the spring located at the back of the rolling direction. And there is the same observation for the sensor which is positioned farther away from the tire's bed. We noticed higher elongations for both springs. In conclusion, two sensor mounting scenarios in tires have been translated into numerical concept tire models, and the results are promising with our technology toolkit and workflows. Our technology toolkit and workflows can be used in the virtual development approach for smart tires development projects and various tire and sensor design sensitivity studies. We aim to develop and use machine learning algorithms and artificial intelligence to collect and interpret more synthetic data from the virtual sensor signals for smart tire system validations. We also aim to develop other vehicle dynamics algorithms based on the full vehicle virtual models and real-time vehicle dynamics data generation from the virtual sensors. Thank you for your time. You can contact me through various communication channels to continue this technical discussion. I'm looking forward to hearing your questions about these applications and other potential ones for our technology toolkit. Stay tuned.